In section 9.1, we learned two formulas for calculating the sample size. One was for calculating the sample size for proportion if you have a prior estimate, and one was for proportion if you have no prior estimate. But the question becomes, what if it's not for a proportion at all? Proportions are things like samples and polls, when you want to call people up and say, you know, who are you voting for in the next election, stuff like that. But what if you want to estimate a mean? I want the average body temperature. I want the average lifespan of a tire. I want the average thickness of a bottle of laundry detergent, etc. Well, if you're going to do it for a mean like that, an average, then you want this formula from section 9.2, which is n equals z alpha over 2 times s over the error squared. So let me grab it right here. And you're always going to round it up, just like the other ones. All sample size formulas are always rounded up, always. Okay, so we want to estimate the loss per pickpocket crime in the US. That's what we want, just to make it up. How large a sample is required if we want our estimate to be within $50 of the actual population mean with 90% confidence. So that within $50 business, that's your error. So the error is the within part. So look for that in these problems. In this case, it's 50. All right, so we're going to use that in the formula. So let me grab the formula real quick. All right, so now I want to know n, I want to know n, so I'm going to figure out s and the error and the z. Well, we already know the error. The error we just said is 50, so that's not too bad. And the s, we actually calculated already because we already had this data set. So this was given to us from earlier, so I'll just write it down now. S was calculated earlier to be 262.23. So we calculated it when we ran one variable stats. It's also still sitting here from the confidence interval, 262.231 if you like. So 262.231. It was calculated earlier using one variable stats. Sometimes they'll just give them to you in the problem. This particular one did not, so that's fine. So we'll put in 262.231 right here. And that leads us to our z-score. Now we got to go and figure that out. All right, well, why aren't we using t? Well, you're not using t because t is based off of degrees of freedom, and degrees of freedom is based off your sample size. And since you don't know your sample size, you're kind of out of luck, right? So your confidence level is 90%. That means that your alpha is the complement of that, which is 10%, which should be 0.10. Okay, then that means that alpha over 2 would be 0.05. Now I'm about to make you very happy campers. Now we actually found this one back a while ago, back in section 9.1. It was right there on that page. 90%, we did inverse norm, we found 1.645, blah, blah. And if you remember at the time, I said, don't worry about putting these three numbers on your note sheet because there's another way to get them. And I'm about to show you how. So let me grab the t-table for a second. So if you look at the t-table, and you look at your degrees of freedom, and you let your n, i.e. your degrees of freedom, -1, get larger and larger and larger and larger. Look what happens at the very, 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 very bottom of that table. Do you see it? That's the letter z. That's standing for n is equal to infinity, because at your, degrees of freedom being infinity, that would be your z value. So what was the alpha over 2 that we just said? Alpha over 2 was 0.05. Let me scroll down to find that problem again. Hold on, it's going to take me a minute. Boy, we've covered a lot of material since then. All right, 0.05, there it is, 0.05. So I'm going to go to the 0.05 column. So let me type that in. Go to 0.05 column in the t-table, believe it or not. And you go to the z row. Go to z row in t-table. which is the bottom row. And look what you've got. Okay. It should say 0.05 column in T table. There we go. All right, now the Z row, I keep clicking on the PDF. It's not the PDF. There it is. The Z row is 0.05 down to the very, very, very bottom, 1.645. Looky right there. That's the one that we got back in section 9.1 using inverse norm. And while we're on the subject, 95% was 0.025 for alpha over 2. And look at the number. It's 1.960. So you actually have a quick reference with this table to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 different z-scores. Now, will I give you one of them for sure that is not in this table? Yes, I will. You will have to find one of them at least on the exam using the old inverse norm method. Okay? But once you found that one with the old inverse norm method, then everything from there is great, right? So if you want to use the table for any of the other ones, as long as I don't mind and I say don't find it by hand or whatever, then you're good. You can use that table for any of them you like, as long as they're in there and I don't specify otherwise. You're welcome. Okay, so you go to the Z row in the T table, and it was right there. You find that Z alpha over 2 is equal to 1.645. All right, so now I'm going to use that value and substitute it into my equation over here. So I'm going to say this is 1.645. All right, so I'm going to grab a calculator and type that into it. So I want, clear this, parentheses, 262.231 times 1.645 divided by 50, close my parentheses, and then I want to square it, enter. And I get 74.432. Technically, all of this is approximation because we're rounding our S values and we're rounding our Z values. So I will just leave it like that, which means that it's about 75 because remember, we always, always, always round up. And there we have it. Sorry, I just had to rearrange that just a little bit. So here's my error. That's the within part. That's 50. And then I had my S, which is calculated earlier, my confidence levels right here, my alpha's 0.10. Then I learned this new trick of if I don't want to use the inverse norm, which you could use it, or inverse norm 0.05, norm 0.95, right, comma 0, comma 1. So if you want to use the inverse norm or the T table, the Z row of the T table, either one's fine, you'll get your Z value to be 1.645. And again, I warn you, I will give you one on the exam that is not in that table that you will have to use an inverse norm for. All right, then you substitute in your values, which I guess I don't need this to be quite so far away. And then I got it to be 74, and then I rounded that up to 75. Always have to round up. All right, now what would happen if I raise my confidence level? So let's go back and look at that table some more. So over here on the left, I have the low confidence level values. Like for example, we were at 90% with 0.05. If I want 95%, that would be 0.025. If I want 99%, that would be 0.005, right, and so on. So if you raise your confidence level, look what happens to your z-scores. If you move to the right on this table, look at the z-scores. They get larger. So if you raise your C level, your confidence level, your Z values get larger. And that would make the whole fraction get bigger because Z is in the numerator, which means Z is directly relational to, has a direct relationship with N. So let me type all that up 1 second. All right, there I have it typed up. If your confidence level is raised, that will cause your z-value to be to a higher number. Remember from the table, higher numbers on the right, those are bigger confidence levels because they're smaller areas in the tail. So bigger confidence level makes bigger z-value. The z-value is in the numerator, right? And since that's in the numerator, it will cause your n overall to get larger. If your numerator gets bigger, the number gets bigger. That means that both z and s, because they're both in the numerator, have a direct relationship with n. In other words, if z is bigger, larger, then n is bigger. If z is smaller, then n is smaller. They go hand in hand like peas and carrots. Now, what about error? Well, error is in the denominator, so it's going to have the opposite relationship. It's called an inverse relationship. So if you lower your margin of error, right, in other words, you want to shrink the size of your interval, you want to be more accurate, make that target, that bullseye target smaller, that's going to cause your n to get larger because it's in the denominator. Remember from grade school, hopefully somewhere, you learned that 1 over 2 is a bigger number than 1 over 10, say. This has a bigger number in the denominator, it makes it smaller overall. So if I lower the number in my denominator, it's going to make a bigger fraction, right? Right? And that means that e, the error, because it's in the denominator, has an inverse relationship with n. If e is larger, because it's in the denominator, it makes n smaller. If e is smaller, it makes n larger because of this property of fractions. Right? Okay, so we're done with looking at sample size. We got a little bit of something to think about there for how these formulas work. And by the way, this isn't true just of these formulas. If you go back and look at the other sample size formulas, see z and the error in there, see them right in here? They have that same relationship. Z has a direct relationship with sample size, and the error has an inverse relationship because error is always in that denominator. To be honest with you, we don't really mess around with s. So I'm just going to say z. Z has a direct relationship with n. Okay. S is the sample standard deviation. You don't really play around with that so much. But you do play around with z, your confidence level. So if z gets larger for 1s and 9, 1, it makes the overall n larger. Same here. If z is larger, then n is larger. That's because z is always in that numerator, always. Look at all these. And then error is always in the denominator. So error is opposite. You get your interval more accurate, make your error smaller. It means you're making your net smaller. To do that, to get away with that, you're going to need a bigger sample. All right, we're all done with that sample size bit. And I'll see you back here to read a computer output of another confidence interval. So I see you then.